Central.
So that's central.
So for every 100 people, there's 100 questions.
What?
Just like whatever.
And then have a series of options.
So you need to know how you.
I'm not very
Did you couch surf a little thing? Did you crowd surf a building?
Come on, I know I have a mask and gray hair, but I'm not that old.
Okay.
Oh, yeah.
You just took all your weight right there.
Trip forward naturally, I was like.
Yeah, the first rule is when you're falling, do not do this. Fall into your shoulder, because, worst you do is you dislocate it. Snapping every bone here, which is what you do.
If you're thinking that, rookie logic of falling at that point. Everyone knows that.
Hello, everyone. I have two sets of quiz.
May or may not have my test.
Review.
Do you know which number you want?
First one, which word has to be generated from S? What do you guys think?
I don't even know, man. Yeah, it takes me a lot. It's small thing. Oh, no. What happened? What? It doesn't like. It went away. I give up.
Okay, so you can't generate A, right? Because we can go S to AS, the first one. But then from S, so you already, so you generated A, but then to leave S, right, you have to go to B, right, at some point. So you can generate many A's, but you only need one for that. So you go to B, but from B, you have to generate B prime, right? So and that's so you're gonna have the extra B. Can you generate BC? Yeah. Yes, you go S to B, right? And then B, you do B prime, and then B prime go to C, and C goes to little c, right? C terminal. How about ABC? SAS, and then S going to B, right? B going to be B prime. Then you turn that B prime into a C, right? Because you need to generate another C, so you do, from C you go to C, little c, right? C terminal. And you can do many B's, right? Between A and C. You just need to do that recursive one, B going to be B prime, and then you do B prime, B prime, right? To generate two B's. And then when you're tired, or you need to move on, you go B prime to C, right? Is this grammar regular or non-regular? the left side of the productions, you only have one variable, right? That's good. And on the right side of the productions, you can have a variable, a single variable, or you can have a word in a variable, or a variable in a word. You only have like a variable in the sense that is a word with only one terminal and then a variable, right? So all these productions, they fit the definition of what we expect in a regular grammar, okay? You guys agree? This is a regular grammar, okay? So, still on that same grammar, can you identify the set of variables? All the variables of the grammar.
Got this.
Okay, so the variables are S, B, B prime, and C, right? So the variables are those symbols that you can replace with what's on the right side of the production, right? So those are the variables. About the terminals now.
I'm sorry, if S couldn't redirect back to itself, would it still be a variable? Oh, thank you so much.
That's the question?
Oh, AS is valid, but if there was no S to AS and it was only S to other things,
S is to consider a variable. The start S is to consider a variable, it's the start variable. Variables is not just because they appear on the right side, right? Because you need to start from some point, so you start with the start variable. About the terminals. Terminals are the ones that you can't substitute. Once you reach a terminal, it's done.
Just doesn't like this picture. That's all there is to it. I'm trying to color it in.
Oh, there was the shape.
Yeah, I'm trying to color it in. I'm bad at drawing between the lines. Dude, Bob Ross.
You're gonna lose your
Oh,
attendance
shit.
because of the brightness of the shape.
Happy little trees.
Okay, so A, B, C, right? Lowercase, they're all the terminals of that grammar. I got 82%, so some of you are still not sure about variables and terminals grammar formal definition, so you need to review that, okay? Which is the only words that can be generated from S. all of the words generated by this grammar, they have something in common. What is that? What is the pattern? Right? Still coloring?
This is way harder than it looks.
Just make it.
What do you mean? I'm gonna draw a rectangle and fill it in, right?
A 300 elective course and you're drawing.
I'm failing that.
In his defense, I don't think Metro like offers an intro to coloring.
Doesn't have intro coloring. 77%, the last one.
Apple Master.
So what is something that all words from that grammar generated from that grammar have in common?
They end in 0.
They end in
0,
1.
0, 1, right? Because what are those productions are telling us, right? S is the start symbol. Usually it's the first production, you can figure out the start symbol. And then you have S going to 0S or 1S, right? So it's telling you that you can generate many zeros and ones, right? You generate many zeros and ones, zeros and ones. When you're done, when you're tired, I like to say, when you're tired of generating zeros and ones, you go to S prime. So you turn that S into S prime. From S prime, you can only turn that S prime into 0, 1, right? Because the S is at the end, right? All the words will end in 0, 1.
I thought you were talking about which ones are, why are the wrong ones wrong? I didn't, sorry, I missed your question.
Yeah, this one is the only one that can't be generated. Right? The others, they don't end in 0, 1, so you can't generate those words. Right? How would you describe LG? It doesn't exist anymore, right? LG exists, but it's not producing phones anymore, right? I guess they still do TVs. LG, language generated by the grammar. What's the best option there?
Zero, one.
Okay, so start with X, right? From S, you go to X, Y, Z. So you already have X, start with X, end in Z. Then that Y, that Y variable, you can use to generate as many Y terminals as you want, or none, right? Because you have the epsilon. When you're tired of generating Y's, you turn the Y variable into epsilon. The effect is getting rid of the variable, right? Okay, so we have another set.
We still haven't had a parade.
Sorry, it's hard to read. Okay. 86%, good. 2 went for the excuse me. Just the text of that option is suspicious, right? Why this excuse?
It's suspicious.
Why not just say you cannot generate? Why this excuse?
Excuse me.
Like, it's almost like the instructor is offended, or the student is offended, right?
The question could also
I can't see the whole question.
Yeah, you just have to give us the answer.
I think it's how he described the line.
So it's how would you describe the words that can be generated from S? Okay.
What are the questions?
It's really dark.
Okay.
So,
There. Oh, actually. Oh, you already got my answer and I realized.
okay, so the last one begins with A.
And I realized that right after I gave you C. that
Begins
it
with
was-
B's, and the number of A's should match the number of B's. That's different
The
than
empty words.
words that have the same numbers of A's and B's, because you can have A's mixed with B's, right? And the number matching, right? But that's not that the language for that grammar. It has to start with A's and then finish with B's, okay? Oh, by the way, going back here, do you think that grammar is regular?
No.
It's not regular, right? Because you have a word, a symbol, and a word. You can't have that in a regular grammar. Okay? The regular grammar, you only have productions on the right side having a word and a single variable and nothing after, or a variable, right, and a word, and nothing before the variable. Those are the only two options, or just a variable without word, right? So that grammar is not regular. So there are some grammars, right? This is an example of a grammar that is not regular. Today we're going to discuss those type of grammars. They're called context-free grammar. How about this one? So, by the way, let's just look at the grammar. Do you think that grammar is regular? It is regular, right? Okay. So I'll try to answer that one. Okay, so the words begin with A's, right? And then you have B's, right? Because from S you go to AB, variables, or epsilon. If you go to epsilon, you're not going to generate, you're just going to generate the empty word. From A, you can do many A's. When you're tired, just go A variable to A terminal, right? And then from B, you go to many B's, eventually just one B, right? So you want to generate just one A, you just go to AB, and then A going to A, and then I guess you have to generate a B, right? You can't generate just A, right? What is key comparing that grammar? The grammar is like trying to match what the other grammar was trying to do, right? But one thing that is different is that the number of A's, you can't match the number of B's, right? You can have 2 A's and 3 B's, and have 1 A or, I don't know, 10 B's, right? But there's no way for you to, of course you can match, but that's not what this grammar is. This grammar cannot restrict the pairing of A's and B's. That's what I'm trying to say. Yeah.
Do you argue that that's the best fitting definition, but still not accurate, since it should be like words
Yeah.
that begin with one or more A's followed by
Yeah.
one or more
I
B's?
kinda
and then
agree.
no A's
After-
and B's.
I kind of agree after I was reading this now, because as you said, you can, for example, I can't just generate A's, right? If I have at least one A, I need to have at least one B, right? Because of the A and B. To make that possible, I would have to add like S going to A or S going to B, right? And then I will be able to generate just A or just A's, right? And or just B's. So it's kind of incomplete, right?
Or have epsilon be an option for A goes to A.
Yeah. Put the epsilon for the A and B productions, that too. Okay? So I will rewrite that to make the more the way is expressed, the language to be more clear. Okay. All right. That was the last one. Good. So let's talk about context-free grammars, right? So one of the examples of that we saw in one of the questions of the quiz showed a grammar that wasn't regular. It didn't fit the definition of a regular grammar. So there are grammars that are not regular, and the superset of grammars that encompass the regular grammars, but they are more relaxed in the way the productions are defined. It's called the context-free grammar. Okay, so a context-free grammar is still going to have productions where the left-hand side of the productions will only have one variable. So we still have that restriction of we had in the regular grammars, where the left side had only one variable. But on the right side, on the right-hand side, we can have anything, basically. Okay? So you see that it accepts A going to some alpha, and alpha, so A is a variable, so it has to be a variable, and alpha is a combination of variables and terminals, right? So you can have a combination of variables and terminals in any way you want on the right-hand side. Let's see some examples. Okay, so this is a context-free grammar because S goes to ASB, and ASB has it's a combination of terminals and variables, single variable S, and two terminals A and B. So you have words, right, on the left side of the variable and also on the right side. So this is not a regular grammar, but it is a context-free grammar. Context-free grammars, they are very important for to formally define programming languages because they allow us to do pairing, right? So that production S going to ASB is very important because we're pairing the number of A's with the number of B's. Every time I use that production, I produce an A, and at the same time I produce a B. Why do you think pairing is important when we define programming languages? Where do we see pairing in common syntax of most programming languages, for example? Parentheses, right? Brackets, right? Definition of block, right? Scope. So this is very common, and we need to have a way to make sure that those symbols, when they are generated, they're generated together, right? So we can verify those things. Here's another example. So now we're able to specify a grammar that allows us to define arithmetic expressions with parentheses, right? So we can think of E as an expression. So an expression can be addition of two expressions, subtraction, multiplication, division, or it can be an expression in parentheses. So, for instance, whenever I open a parenthesis, I should match with the closing parentheses. And X is just a terminal that will be used for identifiers. Trying to make as simple as possible to express like arithmetic expressions. Let's use just one symbol for identifiers. Okay, but you have you start to see seeing some of the terminals keywords that you see in programming language, right? You see operators, you see identifiers, right? And you see these productions here. We're actually going to use that type of specification later when we start writing our parsers. Speaking of parsers, we're going to use a notation to show the derivation of words using grammar's productions. So far, we have been using a notation where we start with the start symbol and then use arrows to show the derivations. Okay, but looking ahead, we want you put all the derivations into a data structure. And the data structure you're going to use is going to be a tree, where the nodes will be the inner nodes, right? So you have the start symbol as the root of this tree, and then you have the inner nodes as the variables, right? And the leaf nodes as the terminals, right? So the parse tree is going to be very useful to represent it's basically going to be the output of the parser. It will be the parse tree that represents a source code already evaluated and with the syntax structure all defined by the tree. So examples of parse trees, let's say I want to do using this grammar here. I want to produce, this is how you read. I'm producing AAA, so 3 A's and 3 B's. So starting at the root, I'm going to apply the production S going to ASB, so ASB. And then you see A is a leaf node on the sparse tree. I can't go further, so it's done. But this S here is a variable, so I can apply again S going to ASB. So it goes one level down on the street. And I keep going until S turns into epsilon because I'm done. So if you traverse this tree in order, right? Notation. So you go A, right? Before you go to S, so it's in order. So I have to evaluate this whole path here. So A, and then B, right? So if you traverse this in order, you end up having the word that you want to generate, right? Well, when we evaluate the parse trees, ideally, you want to be able to always generate the same parse tree. Okay, but there are grammars that would allow you to generate different parse trees depending on the order that you apply the productions. So those grammars are called ambiguous. So the definition for a grammar that is ambiguous, if there are more than one parse tree for a given word. So I give you a word, and one person is able to generate one parse tree. If someone else use a different reasoning, is able to generate a different parse tree because it choosing different order of the productions, how they were applied. That grammar that I mentioned before, the expression grammar, is actually ambiguous. Can you try to generate two different parse trees for this word here? So grab a piece of paper, and I want you to try to generate two different parse trees for this word here. You can use. Now you can use your draw. I said draw the parse tree.
Or no, I haven't done it. I mean, no, I'm in both development. So it might be there. We're using a lot of stuff. No, I don't.
Somebody to verify that.
I'll basically. Philosophy class. Yeah, like the. And I basically have to do an additional semester in order to pay them. And like, I don't know, I feel like.
Yeah, you can do that, SSH.
I don't know. Yeah, I don't know. I won't clear the caps because.
No, you were saying, sorry.
And I think it lists kind of all like literally every.
Yeah, it's the last group.
So I'm doing all the rhythm semester. And my math, I like have all of
Somebody's SSH too, you know.
The partner should be.
I mean, I'd appreciate it.
There you go.
Right now.
Okay, so.
Never do that, don't.
You get it?
Do that.
right? So I don't know if yours look like that one, but here's an example. The one on the left, I applied E plus E before, right? And then the second E, I then did the multiplication. So this is x plus x times x. The other one, I decided to apply E times x first. And then on the left side, I went down and created the E plus E, right? So that's not good. The fact that sometimes we generate one parse tree, sometimes we generate another. And this also has to deal with the precedence of operators. Usually for this particular example, we would prefer this one on the left, because the multiplication has precedence over addition when you have an expression without brains, right? So, but the good news is we can actually use reasoning, creating other variables. We can actually, for most cases, we can remove the ambiguity of a grammar. Okay, so this other grammar is not ambiguous. Okay, so it's also does the expression, formal expressions, arithmetic expressions, but doesn't have the ambiguity. Because when you start with E, it forces you to do E plus term, E minus term, or a term, right? So the term is the one that can go to factors. And factors, so term is term times factor, term divided by factor, and factor. So F is called a factor, an expression that cannot be pulled apart. And then T is called a term, a productor, or quotient of factors. E is either a sum or a difference of an expression and a term. Okay, so where we do that, for example, if we were to do the x plus, can you try to see using that grammar, can you try to create two parse trees? You should not be able to. So x plus x times x, right? Isn't that the words we wanted to use? Right? We try to, using that grammar, try to do two different parse trees. So we start with E, right? And then kind of forces you to do E plus T, right? Because if I do T, if I pick T, right away, after I go to T, I can only do multiplication of factors or division of factors, right? I cannot go back, right? Are you guys seeing that? I have to pick, because if I do E going to, let's say I don't want to do the addition subtraction first. The only option I have is going to T, but if I go to T, I can't show the addition, right? I can't do the addition because T, I can only express this. So there's only one path, which is E going to E plus T, right? And then from T, I can go to T times F, right? And then T can go to factor, right? And then from factor, I go to X, factor, I go to X. This E here, I can this case, my only option is to do a t and then t factor x. Okay, so my parse tree will always be like that. There's no way I can trick and pick other way to create a different parse tree. Okay? So this is a similar grammar. So it's doing the same, generating the same words, but in a different way without the ambiguity. Okay, so before we talk about, is that the last one? How about we do some activity now? Let's open activities. I had a hard time with the printer today. I'm sorry that I didn't bring this activity printed. So just open activity 2 as examples of context-free grammars for further practice. Okay? So I don't know what's the best way for you guys to do that. Maybe download the word and then write directly on your computer.
On campus.
Yeah, Canvas, and then go to in-class activities. Activity number 2. Okay. You all have to be in front. How are you doing?
Just got to stare at it for a minute.
No, I'm just trying to understand why.
Types, right? Yeah. Separate them. Exactly. So the first one doesn't have any options. That's it. That's the whole thing. Yeah.
And then notice the left and right parameters are important.
So, yeah.
So the C out is C out is comparisons to another C. So that's syntactic if statement. So that is comparing two things. So true. No, because look what they are. You got CL. The CL.
Generating dollarization.
It's from the CL line. Dollar and then one of the variables.
That was easy, right?
It's activity, well, we're looking at three.
Activity three.
But are you looking at activity, are we at one too much? You have to look at the.
Yeah.
Oh my God.
No wonder we were lost. Oh.
Oh, this looks so much more less resistant. No, last time we did,
Oh, right.
this is context free.
Yeah.
We're making it work. We're making it work.
Thanks, Harrison. You say. Harrison's like, you guys know.
Like, I'm looking at this, I'm like, it took me a while to get this open.
Dollar signs. Other people, you guys see me right now, right? Yes. Yes, I can see somebody's 6 people to in here. I can see Alex first. I'm here.
Yeah, we're in the view only. Yeah, it's view only. We can't edit it.
So I changed that.
It's kind of.
Okay, so yes for the
Okay.
first one.
I don't want to do anything in COBOL. I'm not going to touch the mainframe.
It's okay.
All of those sound horrible.
Start.
Yeah.
First one was. So then you'll go to S to
Each
A.
S can do it. Why don't you turn this first message?
Go to SS or A.
Wait, which one is S?
You can't have a double A.
A.
You're gonna end up with an extra A.
I mean, you can, let's turn the second message.
Triple A.
You can have a double
Write it out. You can't, because it terminates.
Now you want to.
Oh, wait. Now you want to just try writing it out.
You have to do one.
I'm just trying to look at the sequence of what
This
we're
trend is going to be privilege escalation clearly.
You wanna go yes? Okay, cool. You can't do double B either, so it's just low.
So, wait, are you saying that A works?
That's terminates A.
So when you do the derivations, try to apply one production at a time to avoid getting lost, okay? Try to do any productions in parallel. You are not a super GPU, okay? So you only have one processor. So just do one at a time.
First A, second one. A, B,
Yeah. No?
Second B, first one goes to B.
Oh.
Both S's.
I don't think so. Sorry, second A won't be. Well, it's a lowercase. I gotta reconcile. I think I understand. I'm just gonna see.
I know what you said.
So, S. Somebody doesn't even ask. I didn't even see the.
Say so
Pick
on
the other one.
first.
The third one? I'm trying to do this on my head, which doesn't work.
Okay, so this first one, is it a yes or no?
Yeah.
Yes, right? And you can do S going to A, right? S can go to A, that's what we want. How about the second one, yes or no?
Yes.
Yes, right?
Oh, I see, one can terminate, one can go.
Oh, I see.
Okay, so S going to. If I put S going to little a, I'll be done. So I should definitely do the other option. I can turn each A into a B, but I need AAB. I can only produce A's if I go to S. So how about I'll turn the first A, right? Because the A's appear before the B. So I'm going to turn this A here, right? And I'm going to use different colors. So you know what is changing. How about purple? So I'm going to turn the purple, right, into two S's. Okay? Then I repeat the other one. So remember, that purple A became two purple S's. And the red A, the angry A, it's too angry. Okay, do you see the with the colors, you see the changing? Okay. All right, so now we have, I know that I can turn each S into an A. I need two A's. I'm gonna turn the first S into an A. And I'm gonna do one at a time because I don't do multi-programming. I do one at a time. Turn the first S into an A. Now I'm going to turn the second S into an A. A. Still have the angry A here. Okay. I'm almost there. I have two A's, but I still need a B. But I can turn the A into a B. So finally, I can do this. Okay. All right. So in an assignment or in an exam, if I ask you to do something like that, I want to see one step at a time, just like I did here, okay? Because I had some students in the past that when I asked this in an exam, they did yes, and they simply did this. And when they are,
But that doesn't.
when they want to do a little bit more, they would put exclamation and then say multiple productions.
Which productions?
At least they didn't just take trivial.
Yeah, they did that. So,
The Cleany Star.
so it's like in Brazil, we had a TV show, like a comedy show, that the setting was like a school. They were all adults, but they pretend they were in an elementary type of school. And there was this guy that whenever the teacher asked a question, he would do everything except answering the question, right? So it was they call him somebody love, right? So somebody love is like you try to show that you're answering, but you're not answering. This is an example of a somebody love. Don't do that. Okay, so this one here. Yes or no? I think it's a no. Were any of you able to do it? Okay. I know some of you are math majors, and what we're doing here is like, we're not proving that it's impossible. We're just saying that we couldn't do it, right? It doesn't mean if we don't formally prove it, it doesn't mean anything, right?
Doesn't there have to be an odd number of terminals?
Yeah, you can try to not providing a formal proof, but at least you can describe that why it's impossible, right? And the reason is, whenever you generate S, you can have a single A, but if you go here, right, you're always going to have pairing, right? So you can have have a single A or words with an even number of terminals, right? Oh, but the A go to B, right? How would you describe that?
A single A or an odd number of terminals where the amount of A's and B's are not equal.
Because the A can turn into two S's, right? And the S's can go to B. No, the S's can go to A.
You could have 4 A's, I believe.
Say that again, Letitia.
Oh, I know this. That's wrong.
You can start trying, right? So if you want to generate this, you have to do S going to A, right? So let's try. Then we're gonna reach a dead end, right? That's the only option to go. That A. Well, we can't turn this first A into a B because the word doesn't start with a B. So we have to turn that A into SS, right? And then, okay, the first S, okay, we're gonna turn into A because we need that A, right? We're gonna have this. But now we need a B. That S needs to be turned into AA, right? So now I can turn that first A can turn into a B. Now I have AA. Now I need an A. So that A I need to turn into S, right? To two S's, right? That S can go to an A. Right? But then well, I need to turn that S into two A's so I can turn into a B. Right? Is that right so far? I can turn that A into a B, right? A, B, B. But then I end up with two A's. What am I going to do with those two A's, right? I can't make them disappear, right? So if this is a kind of demonstration, right? Because I tried, right? We tried to go with the options we had, and this is the only way to go, and I end up with a situation where I can't go further. Okay? How about this other one? Were you able to do it? Yes or no? You did it? Show me the steps.
Okay. Start with S. S goes to double capital A. That first capital A goes to lowercase a, and tack on the second capital A.
A can't go to
it can
A.
only go
Yeah.
Oh, yeah.
Ah.
A can only go to double S's.
You would end up with the trailing S.
Right, so if we try AA, then A So I have to do two S's, right? And then A, S, A. Now we need a B. So S has to go to AA. And then we have to repeat the A. And then AB, AA. So A has to go to SS. Then AB, A, right? SA. And then ABI, ABA, S. I need to turn that into AA, right? So I already have too many, right? ABA. Oh, I was doing the other one. I want to do ABB.
Yeah.
Nobody told me anything. I had, okay, it's ABBA. So I can do AB, B, A, right? Right? But then I need to turn that A into a little a, and I can't do that because I have to do SS. And that's the problem, because AB is A, I end up with an S. I don't know what to do with that S, right? So can't go. All right? Isn't that fun? Build a context-free grammar that is able to generate WW is a word from XY parentheses, any combination including zero, or no word at all, or no symbol at all. But the parentheses, they have to be balanced. So here's a solution. So I can use this one to generate as many x's as I want. And I can also generate as many y's as I want. But when I generate the parentheses, I want to make sure they are balanced. So I will generate this way. And well, if I do that, I can't have anything after the parentheses. I'm going to put an S here, and then epsilon. Okay, so this production here allows me to generate as many X's as I want. This one as many Y's. If I need to generate something with parentheses, but I want to continue after, I can use this one. But if I don't have anything after the parentheses, I can just turn this S into epsilon. But the parentheses will be balanced because whenever I have one opening, I have one closing. Okay?
Is this one only context-free for the parentheses case?
Because of this case, yeah. Right? This is not regular. It is still context-free because on the left side, I only have one variable. Okay. But now we're going to relax even more the restriction of that we had. The only restriction we had in the context-free grammar was what we had on the left-hand side of the productions, right? It only allowed one variable. But now we're going to relax that and say that on the left side, I can have a variable, okay? But surrounding that variable, I can have words. Okay, that will be a context-sensitive grammar. Okay, why the name context-sensitive? Because the production with the alpha and beta surrounding the variable is basically saying that, well, that production can only be applied if the variable A is in that context of having an alpha before and a beta word after, right? So it creates a context of when I can apply the rule. That's why it's called context sensitive. Okay, so here's an example of a context-sensitive grammar. So look at that. And by the way, the alpha and beta, they can be, and the gamma too, right? Can be a combination of variables and terminals, right? Can be anything. So this is an example of a context-sensitive grammar. Because look at those productions here, CB, CZ, right? So all of these productions, right, after the first two productions, all of the remaining productions here, they all have, on the left side, they have combination of variables and words. So how do you read this? Well, what we're doing here, we're changing, so we can only apply this production here if the C, right, variable appears before a B variable. This one can only be applied if the C variable appears before a C variable, and so on, right? So try to generate, get a piece of paper and use this grammar and try to generate 3 A's, 3 B's, and 3 C's. And by the way, you can see the way the language is described here. I'm saying that this grammar is this language here, or generates this language here, where the number of A's match the number of B's and the number of C's. Okay? See if you can, using those productions of a context-sensitive grammar, see if you can generate 3 A's, 3 B's, and 3 C's.
It's the second star terminal. I didn't even see that. Three K's is unique.
is so painful.
I see. So. Right, which. That's not really.
This is where the problems are. And then it'd be a big thing because if you use those middle productions, you can flip a CB into a BC. Our problem. So you've got big B right here, little B, little B. You can do that. Big C. Same thing. Is CB. Call the option out. This is a
So let's try.
It's like if you go to twice, you end up with AASBC.
Yes.
The trick is you have to carry just do both BCs.
Well, I'm going to start with the second production. ASBC. Then I'm going to do it again.
So you're saying that it solves.
Okay. So now it's just a matter of moving the big A's or the big C's, right? We want to move to the right and leave the B's in the middle.
Shouldn't that be a lowercase a for the third? Fourth one?
Yes. Thank you. And the last time we do it, the third time we shouldn't do ASBC, we should do ABC, right? So I'm gonna get rid of this S. Okay? So ABC is the first production, turning this S to ABC. So maybe we should do CB to CZ, right? We have to believe that this is going to lead to this. So CB, right? I'm turning CB into CZ, right? This is what I did. We have another CB. CB into CZ. No more CBs. What should we do now? CZ? CZ into WZ? I don't like this B here. So CZ into WZ. Now we can do WZ, WC. Okay. WC into BC. You have to have faith. WC into BC. Ah. WC, BC.
Repeat one more time that CB is.
CB again, right? CB and CZ. Sure.
You just skip ahead.
Yeah.
CCC.
Is this the rest of the class?
Yeah.
CZ, WZ.
No.
WZ, WC. WC, BC. that. BBC. Good, so now we can start doing AB, AB. BB, BB. BC, I already know it's gonna work. BC into BC, and then CC into CC, and CC into CC. Look at that. Wow.
The whole enchilada.
Beautiful, huh?
Sir, I don't think I can do that.
Excuse me,
You want mine.
I don't think you can do that.
But I'm sure most of you weren't believing that this would work, right? Yeah, it worked.
Well, it means CB becomes BC, so then you can just kind of like an abacus, just like switch all the B's as far over
That's probably what's gonna happen.
and then just fill it in.
Yeah, but you can't have a production like big B going to little b, right? Because you can only turn big B into little b when they are in this context here, at the end. You can only do the turn is at the end. If I have a big B going to little b, just that production, what would prevent me to turn this B here into little b, right? And then I will potentially be generating words that weren't part of the language. So the context is key here.
Yeah.
You agree?
Yes. I agree with what you said.
Yeah, but I'm not expecting you guys to come up with a grammar like this. And I got that from the textbook. I didn't invent this, okay?
Is there some,
Just to show an example of a context-sensitive grammar. But to be more pragmatic, this is more theoretical. We're not going to be using context-sensitive grammars. For the programming language, we're going to start thinking about implementing the compiler. We're going to be using context-free grammars. Okay, so this is just to illustrate. Yeah.
is there some theoretical reason why you can't just have big C, big B go straight to big B, big C, why you have to have all the intermediate steps?
Why these steps here?
Yeah, rules 3 through 7. Like, why couldn't that just be one rule, CB goes to BC?
Going from CB straight to BC, right? Why do you have all these steps? I would say to create a context to avoid, maybe if you had this, I'll have to think more deeply about it, but if you had this direct, maybe there will be a situation where you shouldn't be applying that rule too early. But I'll answer your question maybe on Thursday. I'll have to think about it, try to rewrite the grammar and try to see if there is a particular reason why you have this intermediate step. Initially, I would say just to create a context to avoid you going in unpredictable ways. Okay, but I'll think about it. Okay. Now, we just need to talk about a different way, different formality to represent grammars in a more compact way. It's called the BNF. this material is not on slides, is on the resources. If you go to EBNF, there's actually the standard here in zip PDF, so large file. But you can just click on EBNF guide.
The guide.
Not the EBNF God, the God. This is the BNF God, actually. John Backus and Peter Awards, they wanted to come up with a way to improve how programming language syntax were described. I don't know if you remember when we were doing that historical overview, and actually I mentioned Backus because he worked on the Fortran specification and then later on, I think it was Ada. So he learned as he was writing compilers, and he came up with a more compact way to describe language. And this standard is still used today. When you want to learn a programming language more deeply, the first thing you need to look for is the BNF of that programming language, and you most likely you will find it. So it's proposed in, so actually not Ada, Ada came after, it was actually Algol. So he proposed in 1958 to implement Algol 60. That was when the first BNF was first used. So it's very similar to how we're doing the formal grammar definition, but it focuses more on the productions. The formal grammar definition, you have those four sets, right? You have the set of variables, you have the set of terminals, you have the set of productions, right? And you have the start symbol. Backus thought that all of those things are implicit. If I just give you the production, you can figure out which one is the start symbol, what are the variables, which one are terminals. So you don't have to be that formal and specify set notation. You can just go ahead and represent the grammar syntax just by the productions. So that was the first thing he did. And the syntax rules, the productions that we were talking about, is basically a symbol and an arrow or an equal sign and a list of terms. So symbol is going to be a variable because we're going to focus on context-free grammars. So on the left-hand side is always just going to be one symbol. Then you have a combination of symbols and terminals. So symbol is a variable, a non-terminal symbol. List of terms is a combination of variables and terminal symbols. We're going to use the pipe symbol like we're using, right? For when you have multiple options for when you go from one variable, you're going to show multiple productions from that variable. You're going to use the pipe symbol. The arrow can be replaced with a call equal or just the equal symbol. And then we're going to have special symbols that they will be very useful. When we want to say that a part of the list of terms, the right-hand side of the production, has some part that is optional, we're just going to use the straight brackets. So straight brackets is the symbol to represent something that is optional. Sometimes we want to do repetition, and this is something that usually when we want to do repetition, we have to create two productions, right? Or we create a production that has the same symbol on the right-hand side, so we can have repetition, and then we have epsilon. The way he described repetition, it will be using the curly braces. So the curly braces already imply 0 or more. So whatever is inside curly braces implies that it's 0 or more. So you don't have to worry about specifying epsilon. You just put something repeats, but it can also not happen. You just put inside curly braces. You can group options using parentheses. And those symbols, actually, they are universal. You see those when you write regular expressions. For example, multiplication, the splash symbol represents 0 or more occurrences. The addition symbol is 1 or more occurrences, so at least one occurrence. And the question mark means 0 or 1. It's also part of that is optional. So we're going to use, usually in this course, I don't do, if you want to do comments in EBNF, you would put inside parentheses splash. Usually we don't do that. Usually we try to use names for the symbols that are straightforward, just by reading the symbol name. And by the way, in grammar form notation, we like to use caps for variables and lowercase for terminals. Here, we're going to actually write a word that describes our variable. So instead of using E, we're actually going to write expression. And to avoid confusion, right, because we have EX, is E a variable and X another variable in the word expression? No, whatever is in angular brackets is the name for the symbol. Okay, so it's kind of obvious, but we need to formalize and specify all those things. And another important thing is that sometimes we want to use symbols that are special, like the brackets, the curly braces, right? Those are special symbols in the EBNF. How are we going to make the distinction between a bracket that is a terminal and a bracket that symbolizes optional, right? So we're going to put terminals inside apostrophes. Okay, so let's take a look at an EBNF. This is EBNF in EBNF. We're not going to look at this example now. So here's this example here. And I'm going to relax a little some things. It's kind of obvious that if statement is just the name of the variable, because on the left side, you're always going to have just one variable. If you want to be more strict, you can put inside angular brackets, okay? So we have an if statement. I'm going to use equal as the production arrow. And then this if here, right, if is inside apostrophes. So it's a terminal, it's a word, right? A symbol of our language, right? So if is a terminal that represents a keyword in our language. Okay, so that's why it's inside apostrophes. And then we have a parentheses, opening parentheses inside apostrophes, because this is part of the vocabulary of this language. It's a symbol, keyword of this language. And then inside those parentheses, we're going to have an expression. So it's obvious that this is a variable. It's not inside apostrophes, right? So we're going to further later define what is an expression, right? And then we have another terminal in a statement. Statement is another variable, right? And the else part is optional. So that's why we have them inside the straight brackets, right? So this part of the production is optional. It might happen, it might not. It might appear or it may not. But if it appears, it has an else and then followed by a statement. Okay? Identifier list. What is this production is expressing here? is expressing that an identifier list is an ident list or identifier list is made of at least one identifier followed by one or more identifiers separated by a comma. So this part that is inside the braces, it means that it can happen 0 times. So the identifier list will only have one identifier, or it can appear multiple times and all the identifiers will be separated by comma. Okay? Here is an arithmetic expression, can be an identifier or a numerical literal or an arithmetic expression. And then I want to group the operators because I need to pick one of them between the arithmetic expression variables here, the symbols. So I use the grouping to express that all of this part of the production is, I need to pick one, right? So that's why I'm using the pipe symbol here. It's a very compact way to express syntax. Okay, so we need to get used to eBNF because we're going to use eBNF to when you start writing your compiler. So while statement, right? So it's easy to understand the syntax, don't you agree? When we rewrite them in eBNF. Okay, so that grammar that we discussed, the expression, arithmetic expression in BNF, this is how it will look like. An expression is an expression plus or minus a term or a term. A term is a term. Multiplication or division factor or a factor. A factor can be an identifier in literal. An identifier for this grammar is just one letter. And literal can be one digit or more, right? But it has to have at least one digit. And a digit can be all these terminal values here. eBNF, they're great to represent syntax, right? But later, there are some rules, they're called the semantic rules. Those are harder to represent, and eBNF will not be enough to represent semantic rules. So eBNF, which is E is for the extended BNF, and this is the BNF we're going to talk about. That's the BNF that introduce all these symbols that allows us to do repetition in a very compact way. But basically, they are very helpful to represent syntax, but when it comes to semantics, we need something else. But we're going to talk about that in the future. Okay? So, please do another read on your own time about the eBNF, all the definitions here. I would recommend you guys to read and become familiarized with the eBNF because starting next class, we're going to start using eBNF to learn the syntax of the language that we're going to start writing the lexicon analyzer first and then the syntax analyzer. Okay? Okay. That's it. I'll see you guys in 30.
Well, I think the only reason that we're able to breeze through it is because it's in a symmetric fashion. Our heads into intro to